Hi, welcome to Chem 2005. We will talk today about Pyrrol, how to synthesize Pyrrols, and other 5-member rings. Remember what we was talking about the Pyrrol? Okay, has this general structure. Okay, and the most important fact of Pyrrol is that it is electron rich, as we explained in the last lesson. And for this reason will be very effective in electrophilic aromatic substitutions and will work quite badly in nucleophilic aromatic substitutions. Okay, then how we can synthesize Pyrrols? Well, first we can do a retrosynthesis. Okay, and in order to do a retrosynthesis, what we need is to check which functional groups we see in Pyrrol. Okay. If we check, take attention at this thing, okay, what is this? This is not any more than an enamine, isn't it? And what is an enamine? Basically, an enamine is formed by an amine plus a carbonyl group. Yeah? That means that we can break this, and what we can do is I put a carbonyl in this position. Okay. And this can come from the formation of the enamine between this amino and this carbonyl group. Okay? What next? Well, if we analyze the structure, what we saw is that here we have another enamine. And basically we can do the same than before. This can come from the addition of the amino plus the carbonyl group. Okay? This is one of the basic syntheses of Pyrrol. What we need to synthesize a Pyrrol? Basically what we need is a 1,4 decarbonyl compound plus an amino group. Okay? Could be a primary amine or could be ammonia. How we can synthesize the 1,4 decarbonyl compound? This is, Bruno explained it in his lessons, but basically the most common way to synthesize a 1,4 decarbonyl compound is by a Michael addition of Paal reagent. Remember what means Paal means that we inverted the normal chemistry, we inverted the reactivity, okay? And for example, we can take a easy example. We want to synthesize this one. This one, for example. This can be synthesized by, and check, you need to check the notes of Bruno. This can come from this alpha beta unsaturated ketone plus the addition of this DTN. We make the ion of the DTN, and this will attack a Michael addition. Then we remove the DTN and we put the carbonyl group, and we will get the 1,4 addition. Okay? Please remember this because it's very important. How to synthesize 1,4 the carbonyl compounds because it's from where we will start to synthesize pyrrols. Then how we can synthesize pyrrols with this 1,4 carbonyl compound that we already synthesized plus an amine. We will put an example, we will do the mechanisms step by step. We want to synthesize this pyrrole with 2 metals here, okay, and here we will put another metal. How we can do it, okay? We will start from this 1,4 decarbonyl compound, okay? Remember, if we do the recrosynthesis, we will get this 1,4 decarbonyl compound plus the amine, in this case, methylamine. Okay? This type of synthesis always will require acid. Why? Because what we are forming is enamines. That means, remember what we explained in the last lecture about enamines, that always require pH between 4 and 6. That means we want something little bit acidic. And what is happening is that basically when we add acid, first step, always is the protonation of one of the carbonyl groups. Okay. Why? In order to make this carbon more electrophilic. Now the amine, the pair of electrons of the amine will attack and we will form this intermediate. We remove the proton here and we put the proton here. Why? Because we want to eliminate water. Okay, remember that the OH is a very bad leaving group. That means we have to motivate this hydroxyl to leave. The way of motivation is to protonate, making water. And what we have is this. Okay? And now simply the water is departing, and what we have is the formation of this carbocation. That next step, the pair of electrons of the nitrogen are coming here and we generate we lose a proton and we get the imine. Okay, we are almost in the half of the reaction. We have been formed the first imine, and then what is happening is basically tautomerization. Imine enamine, I tautomerize, I generate this intermediate, and then another proton is activating the carbonyl group, and what is happening is that the pair of electrons of this amine are attacking intramolecularly to generate this cyclic compound. Okay? Again, we move the charge, we remove the charge of the nitrogen and we put it in the wedge. Why? The same than before. Okay, what we want to do is to eliminate water and form the imine here. We generate this. Okay? And the water is eliminated. We can form, in this case, the imine directly. And what we got is we get this iminium. And now a second automerization. Basically, we lost a proton, and what we generate is the final Pyrrol. This is how we synthesize pyrrols from 1,4-decarbonyl compounds. Okay? What is important? The mechanism is very easy. Basically, it's the formation of two imines, and then we tautomerize. But the most important is when we will use this synthesis. Well, you know that synthesis is not a sure science. It's not always the same, but a good indication is that this synthesis will be very appropriate when we have this type of Pyrrols, okay, where we have substituted the first and the last positions, CO2 and C4, okay, and these two positions are hydrogens. When we have this Pyrrol, my recommendation is that your first attempt has to be to build this Pyrrol, to synthesize this Pyrrol from a 1,4-decarbonyl compound. Okay? Well, we can do exactly the same to form, for example, furans. Well, in order to synthesize furans, basically what we do we have the furan, okay, and this can come from exactly the same than before, 1,4. The carbonyl compound that we will synthesize by the same way. We can do an analogy. Okay, what is this? This is a enol ether. Okay, remember the enol ethers are formed by the addition of an alcohol to a ketone. Okay? And here we have another enol ether. We can start from the 1,4-decarbonyl compound, and the only that we need is to add acid. Okay? First step, tautomerization. Remember that the tautomerization is catalyzed by acid. Okay, we have this tautomerization, ketone, enol. Okay, the tautomerization, and now this proton, what it's doing is protonating the other carbonyl group. Why? Because we want to do this carbon more electrophile. Because we want that this carbon being attacked by an alcohol. And we know that alcohols are very weak nucleophiles. That means that we will need to activate this position. We activate this position, and what we get is this. And now the pair of electrons of the alcohol will attack here, and we will form this intermediate. This intermediate, again, what we will do is to transfer this hydrogen, this proton, from this position to this position, because we want to eliminate this alcohol here, and what we will get is, we generate water here, water is leaving, and what we have is a carbocation here, and then simply elimination of this to gain the aromaticity, and what we get is the final compound. Okay, basically in order to synthesize a furan, the only that we need is to have a 1,4 carbonyl compound and an acid, and what we will get is the furan. Obviously, it's not so easy. That means in the real life we have to add acid, heat it. It's like we need quite harsh conditions, but we can get the furan. This is the mechanism to get furans. If we want to do exactly the same, but to get thiophens, okay, thiophens, thiophens. We have two options. One is basically we will start with the same. With the 1,4 carbonyl compound. Okay, and we add hydrosulfuric acid, okay, this compound, and we follow exactly the same that we did with the amine, okay, only substituting the amine for this thio compound, thio acid. Okay, second option is that we can start from here and then add Lawesson reagent. Okay, checking the notes what is Lawesson reagent, but basically what is doing the Lawesson reagent is substituting these carbonyl groups for thiocarbonyls. Okay, and then what we do is we add acid and we follow exactly the same reactivity, the same reaction mechanisms done with the furan, and we will get exactly the same compound. This is on the notes. Please try to do it at home, try to reproduce the synthesis of thiophens by the two ways, by adding hydrosulfuric acid or basically doing the D-thio carbonyl groups, following, in this case, the same mechanism that we did in the case of the mean, and here the same mechanism that we did in the case of the Fourier. Okay? And that's all about this type of synthesis of Pyrrols. See you in the next lecture, where we will explain another method to synthesize Pyrrols and when we need to use this other method. Thank you very much for your attention, and see you soon.